Good morning, everyone. I am Kim, and we're on our fourth webinar for the MOXXI webinar series winter edition. Before introducing our speaker for today, let me introduce first MOXXI. So MOXXI is a community of researchers with 150 researchers for more than 40 countries that who promotes the advancement of novel observational techniques that leads to new sources of information to help better understand hydrological cycle. For the past years, we've conducted a lot of activities, and in the past months, we conducted this series of webinars that started last summer with the summer edition of this webinar series. And then now we are on our last webinar of the winter edition. We also has been conducting meetings during the EGU conference last year, and our first ever MOXXI session on advancing on advanced technologies in hydrological monitoring, and participated in the last IAHS conference 2025 in Roorkee, India. Recently, we participated in the IAHS Academy in Ningbo, China, to help share the advancement in hydrological monitoring by conducting workshops. And if you're not yet in our newsletter, please join our newsletter by using this QR. And see you in EGU 2026 in our session, and hopefully also in the MOXXI Splinter meeting. For this morning, we have Professor Salvatore Manfreda, who is a full professor at the University of Naples, Federico. He has past roles at Princeton University and the University of Basilicata, and as visiting professor at KIHM. His research covers distributed hydrological modeling, flood risk, stochastic hydrology, river, and US-based monitoring. He has more than 210 publications and also served as editors in Elsevier books, and currently chairs IAHS MOXXI. He is also in the WMO HydroHub and serves as an editor in multiple journals. Without much further introduction, I give you all with Professor Salvatore Manfreda.
Thank you very much for this kind introduction, and I'm very glad to see that we have a large number of participants. I'm glad to close this series of webinars with an overview of the activities that we are carrying out as a research group, the HydroLab in Unina. But I have to say that I've been lucky in this path of research, because we had the possibility to collaborate with several researchers around the world. So this is not the presentation will not just be an overview of what we are doing, but is an overview of large cooperative research. Within today, I tried to somehow introduce the main aspects regarding the innovation that have been introduced in general in river monitoring, and what are, in our vision, opportunities offered by images, so remote sensing in general, algorithms, and the use and the collaboration of people. In this context, the presentation provides an overview of image-based techniques exploiting both UAS camera system, but also remote sensing. The potential of image velocimetry, some applications that we are developing for remote sensing for water quality monitoring. and also the flood detection and flood mapping using satellite products coupled with the geomorphic indices and so on. To start with, I would like to recall one of our successful publication on remote sensing, where we discussed the opportunities offered by UAS versus satellites. In the reality, they both are necessary in hydrology and all other disciplines because they offer complementary options for remote sensing. There are opportunities in close range techniques that offers high resolution, but at the same time we cannot provide observation over large scale without the use of satellites that now are also improving in quality and capacity of monitoring. In the specific context of close range techniques, which are at the core of this presentation and of our activities, there is a large number of complexity in the use of these techniques, which are connected to the physics, to the equipment, the software, the hardware, the design, experiment, environmental condition, and so on. We have encountered several of these aspects, and somehow we tried to harmonize it, to identify guidelines that could be used by researchers and technicians in the use of these techniques, following a clear workflow that starts with a study design, a pre-flight field work, and up to the quality assurance, which is strictly necessary. In this research, we provide some suggestions regarding the checklist to follow in order to avoid common mistakes and to have and to guarantee a certain quality of the observations that we can retrieve with close range techniques. Of course, there is always a trade-off between the type of techniques that we use, and in this paper there is an example of what it might be in a specific case or for a specific application, the limit for the extent of application for close range techniques based on UAS. So generally, based on this this publication that is dated 2015, it's not worthy to go above 25 hectares using this UAS, even if now with swarm techniques, probably this limit can be extended further. One of the first applications that we explored with camera systems are image velocimetry. Image velocimetry are nowadays considered a mature technique, and in this context, we can both couple the image velocimetry techniques with structure from motion for 3D reconstruction of river systems, and this has been used heavily nowadays also for the detecting the evolution of the river morphology and the erosion of river banks in some publication that has been recently presented by Lars Bertrand. This is one option and one face of the medal, but the other face is the velocity measurements, which could be approached with different techniques, radar, image velocimetry, ADCP, coordinate meters. What is interesting in by looking at the literature is that looking at the trend of the literature, the number of applications of image velocimetry are increasing over time. And we can clearly see that there is a refinement of the techniques and an evolution of the quality of the overall results that we can achieve with this technique. So it seems that it's one of the most promising techniques in the field of hydrometry. This is a short video that just shows how image velocimetry based on a specific algorithm, which is the PTV, can work. In this case, the video is not stabilized yet, but after stabilization, we can see how trajectories of the flow of the traces introduced in the field of view could be detected and in order to achieve the 2D velocity map. Now, we explored a lot how to optimize the flow velocity measurements with different algorithms. And for instance, we also try to optimize using a virtual laboratory of digital numerical simulation, how to optimize and what are the optimal conditions for density of traces and number of frames in order to have to reduce computational effort in this type of measurements. Of course, the techniques are evolving, and the evolution can be ensured only if we share data and we share information and tools. And with this idea clear in mind, within the cost-action harmonious, we decided that one step to take these techniques further was to put together all the available experiments based on velocimetry imagery with reference data for validation that could provide a background for testing the different techniques. This is certainly a valuable contribution that has been used by several authors. Then we moved to a new topic and a new aspect of the water, which is also very critical. Can we explore some of the features of the water quality by using this type of techniques? This is very challenging. There is some potential offered in hyperspectral techniques or multispectral techniques. We presented some of these challenges in this community paper, which is nowadays one of the I have to say, fortunately, one of the most cited in Hydrological Science Journal. And some of these ideas are presented in the following. In particular, there is one big issue concerning the plastic. And this is a health concern, it's an environmental concern. We know there are studies from satellites that have identified macro cluster of plastic in the North Pacific that we can identify here, where there have been measurements in terms of density and weight of the mass of this microplastic that is significant and is observable from the space. So there is clearly a significant presence of plastic in the ocean. These microplastics, the macroplastic then evolve to microplastics that can enter in the food chain, and there are evidences that these microplastics are identified in the human brain and the human placenta, which is something that is obviously generating a lot of concern regarding from the environmental point of view. So we need some strategy to control and measure this type of pollutants, and for sure remote sensing can offer an avenue in this context. Of course, we should try to invest on close range techniques like drones, camera systems, and also cell phones if possible. And working in this direction, we can probably identify and build a dense network of sensors across the globe. There are, of course, already evidences in the literature about the spectral signatures of different plastics. There are already algorithms that are commonly used in recycling facilities for the detection of microplastics for recycling purposes, as well as application based on satellites for the marine litter identification. Now, of course, there is a range of plastics and that we can identify, and the range of plastics ranges from micro to macro up to mega scale, which are the classes that could easily be identified from satellites. But the real challenge is to monitor what is happening in the river, because apparently, based on the experiences and the research that has been conducted on this topic, most of the plastic that we see in the oceans is transported to the ocean through the rivers. So we need to work on something that can allow us to narrow the vision of our monitoring system to the river networks. And in most of the rivers that we have across the globe, we can only sense these rivers with close range techniques. Also because the scale of the microplastics in most of the cases can only be detected with these techniques. Therefore, we started to build a workflow in order to collect the data, in order to be able to build a clear annotation of what the data is giving us in terms of pollutants, in terms of type of plastics. Then we have identified a model for the plastic detection, and then there is the need to build a system for plastic detection in real time for long-term monitoring, and eventually use and export this knowledge for citizen science type of application. This, therefore, the first step was try to work on plastic types and on the data annotation. That was carried out identifying 13 classes of plastics. The training and the algorithms that was used for this specific purpose is the YOLO algorithm, which is a very powerful tool in this context. And this is the first application we carried out for data training, where we installed a fixed camera on the Sarno River. The Sarno River is a critical river which became very relevant at the European scale for its level of pollution, and after becoming the most polluted river in Europe in 2013, several actions have been taken in order to recover from this condition. And actually, there has been a lot of improvements in the current situation, but still there is a significant contribution of pollution due to the food production factories that are present in the area for tomato transformation, which are producing a lot of organic content that is contributing to the river, as well as plastic transport, which is not extremely significant as in countries in Asia, but is present and is useful for our application. Now, What we have done with this workflow of activities in combining several databases taken from Indonesia, from Netherlands, and from Vietnam for the training of this tool was to build an optimal algorithm able to detect the different classes of plastic, and that can allow us to have a clear evidence of what is the level of pollution, what is the amount of plastic that is transported to the ocean, to the sea in this case, and provide information that were not available before. Now, the next step, and what are we working on right now, is the development of an app, a cell phone app, that is now ready for this type of application, where we can also gain information from common users. So anyone can contribute to this big project that is named Riverwatch. You can download and have access to this web app through your cell phone, and include your data and your observation regarding plastic and level of turbidity of your river, which will be uploaded in a web portal which is given in this link. This is at the first stage of a project that is that let us build this web app, but will continue in the next 3 years through a new project that is fully investing on the citizen science as a strategy for river monitoring. These are examples of participatory events where schools have been involved in the projects, and I have to say that this is certainly a way to promote the environment and to promote the restoration of rivers, and also to get information about the current situation of the river systems. The additional step that we have in this flow of activities is also try to investigate the capacity and the capability of this proximal sensing in order to assess water turbidity, which could be useful for water pollution from one side, because the turbidity is a proxy for several indices of pollution, including organic matter, but not only, and sediment transport. Here we have a picture where we clearly see an application of spectral index used to identify the level of turbidity taken based on RGB image taken at the outlet of the Sarno River. But this is, of course, easier to be identified with a satellite or a drone. The question is, and the challenge that we have right now is try to transfer this knowledge in a camera system that is in a cell phone or a fixed camera for long-term monitoring. Now, in order to assess and identify the best strategy for long-term monitoring of water turbidity in a river system, we started some experiment coupling different equipment like a turbidimeter coupled with different camera systems on the Boat River, which is one of the most well-monitored river in Europe. With the collaboration of the UAS, we actually introduced some clay, we injected some clay in the river in order to build a synthetic hydrograph of turbidity peak in the flow of this river. This was actually monitored with both multispectral camera and UAV camera, as well as track cameras, and of course, with a lot of complexity that are connected with the radiance, the environmental condition, the shadows, and the river bed, the reflectance, the depth of the water, and all these factors have been somehow taken, represent a significant disturbance in our experiment. But the experiment allowed us to clearly see the capacity of these techniques and the potential of these techniques to trace the event of pollution in this case, which is produced with a suspended sediment that is introduced in the system and is based on the use of kaolin powder. And essentially, we can see here that the red channel, the red band, was extremely sensitive to detect the signal of the turbidity changes over time. We decided to move further in this direction, and we started a collaboration with also TU Delft. And with this group, actually, we started a second activity of field works in Thailand, where we carried out both indoor experiments and outdoor experiments, also to see how this sensor could be affected by light condition and environmental condition. For this purpose, we use in this case an hyperspectral camera that we can see in this slide, and we can see the spectral signature, that is the red line that we see at the bottom of the screen, under clear condition and under turbid condition. And we clearly see that the bands where we detect most of the changes in the spectral signature. So as this also confirms that there are great potential in order to use camera systems for this type of applications. This is not only the only. This is not the only application that we can carry out. There is also the possibility to extrapolate the knowledge that we do have based on remote sensing in order to detect chlorophyll A measurements. And in this context, we also worked on the development of an algorithm based on a machine learning technique using chlorophyll A measurements taken in different lakes, and try to combine this information with remote sensing data in order to achieve to build a model able to represent and describe chlorophyll A content in different river systems. Essentially, we could use this important repository coupled with additional data that provides more than 800,000 water quality data containing chlorophyll A and turbidity measurements. This data is representative of the entire globe, more or less, with good redundancy. And the model right now that we could build is a model that provides a fair description of the chlorophyll A based on satellite data. And this is also work that has been recently available at least in preprint, with a student that is leading this work, that is Hangchit Moe. And the last type of application I would like to close with is the flood mapping, which is also intensively studied with the use of remote sensing techniques. These remote sensing techniques could help us to describe much better the phenomena. And in particular, what we have explored is the large availability of flood observation provided by satellite. In particular, there is a significant amount of data that is provided by Copernicus Emergency, coupled with other repository that provide useful information regarding the flood events. All this information have been processed and coupled with dam-based indices, and combining both ancillary data and remote sensing observation, we have been able to build, based on a random forest, sorry, algorithm, a tool that provides the flood susceptibility using only satellite data, which might be useful and interesting complementary information for flood risk assessment. This is an example of what we achieved over the entire territory in Italy, and it's also a work that has been recently published on Stoughton last year, which provides useful information regarding flood risk and flood detection. With this, trying to stick to the timing requested by the MOXXI webinar format, I come to the conclusion, saying that image-based monitoring techniques allow and enables high-frequency and scalable observation of river processes. There are several processes that could be investigated with a higher level of details with the use of UAS and fixed camera, and also with cell phones. River Watch is not the only application that we could use. There are several applications that also other colleagues have developed, and that could potentially be extremely valuable in our next future, especially with the combination of machine learning techniques that allow us to manage this large amount of information. Regarding the image velocimetry, is now operationally mature, and of course we observed that we do need guidance because performance may depend a lot on optics, illumination, and other feature and parameters such the seeding density or geometry of the cross section. But we start to see that there are already equipment that can be installed and are available for environmental agencies. Close range imagery can help us also and offer a significant potential to offer information regarding water quality. Of course, this is a context where there is a lot of work that needs to be done, and it's a research that is evolving rapidly. I think that it will evolve with the same speed that image velocimetry evolved over the last 10 years. And of course, the water quality is not the only tool that we can use. It's not the only information we can provide. We can also help and support flood monitoring with the combination of satellite and in situ observations, along with other features like the geomorphic features. And of course, in our vision and my personal idea regarding the river monitoring, I think that the challenge is really to build an integration of these tools in something that we can identify as a smart camera system that might allow to build and to provide several features and several parameters regarding the river systems, and where also people engagement and citizens can support river monitoring over time, and especially intensifying observation in space. With this, I think I can close my talk, and thank you all for your attention.
Thank you very much for the wonderful presentation. It's like a lot of topics all at once in around 30 minutes. Now we're now in the question and answer portion. So if there are curiosities about any part of the talk, then feel free to ask your questions in the chat.
I try to summarize. Okay.
And then I will, and then I will try to read the questions so that our speaker can answer them. While we're waiting for the questions from the participants, let me ask a question from our registration form. So there's also some questions there. With all this advancement in river monitoring and machine learning, how do you envision like the next 5 years? So what should the community do in order to further advance in this and reach implementation levels?
Yeah, no, it's true. In the reality, there is still a lot of work that needs to be done because there is need for improvement of the quality of the data, especially for all the data that is provided by citizens, because there is a lot of potential there, because citizens and participatory approach can help us to monitor the system very carefully and in reaching places that we will never be able to reach with traditional techniques. We are observing already the potential of this technique with the plastic pollution, because promoting the use of these techniques allowed to identify cluster of plastic that were present along the rivers that were not visible from fixed station, or that could not be detected from satellite. Of course, challenges. What is the biggest challenge? The biggest challenge is the quality assurance. So try to provide and assess the quality of the results under different environmental conditions, because environmental conditions can change a lot moving from one side to the other. So, and try to guarantee and allow transferability of these models worldwide is extremely challenging, and it's one of the big issue that we have to solve maybe in the short term.
Thank you. So yeah, for the participants that are also in this webinar, then now we know how to move forward with all this generalization capability, transferability, and yeah. Okay, so we have another question from Ayla, if I read it right. Thank you for the excellent presentation. You showed very interesting examples of remote sensing applications. How precisely can flood extents be determined based on satellite images?
Yeah, this is a nice question. I understand that I couldn't. The intention of the presentation was mainly to provide an overview of the potential of image remote sensing techniques in general, both close range and long range. And I didn't provide many details about what we have done, and now we realize a specific product. What we have done is essentially the following. We assume that we can learn a lot from what we observed from satellite in terms of flood occurrences. And therefore, we started to collect all the observations of historical events, not just as we used to do in the past. We are used to collect the flood peak in a specific point, which is useful, but has a lot of limitation, while we have the information of the flood events observed and the flood extent observed from the satellite. This 2D map, which is in the reality a 3D map because it's a cube of data where different layers of flood are occurring in different spots, offers the possibility to train algorithms, and in particular machine learning algorithms that can understand or can be trained based on what we have observed to identify what are the areas and the conditions that lead to high risk of flood. What are the conditions? The conditions that we have identified are preconditions, and in particular, one of the preconditions we used is the geomorphic flood index with other features such as rainfall and other characteristics, but the history of flooding was the elements that was used to understand the flood susceptibility in space and time. I see another, so I hope I was clear enough, but of course there is a paper where everything is better explained.
Thank you. Another question is from Hassel. Thanks for this great overview. Maybe a question from the industry. What, in your opinion, should industry and NGOs that already provide services and products related to image-based techniques do in the forthcoming years?
From NGO perspective, I think that NGO can easily join some of our projects, such as Riverwatch, but there are also other projects where there is a citizen science approach in order to build a large-scale repository regarding water quality and water pollution. And putting together these informations might become extremely critical and valuable to train next generation algorithms, because we are in an era of large data availability, and where computers can manage large data sets to build a model that are all data driven. In this context, the construction of reliable and redundant data set might help us in order to achieve a more robust approach. Regarding the industry, I think that the industry can also take advantage of this research and innovation and can build upon this knowledge tools and shelter tools that can also be distributed in order to improve quality of observations. And eventually invest more in these techniques that can lead potentially to very low-cost devices.
So from general questions regarding industry and NGO, let's move to a question about geomorphology from Asif. I have a general question regarding the river geomorphological analysis, especially during the extreme events in alpine regions. Have we implemented these algorithms in any of the studies, or can this be found in literature?
Regarding this question, I think okay. Regarding this question, yes, there are several applications, and I think that especially geomorphological analysis are particularly profitable in mountainous regions. So there are applications that have been done in this context, and you can easily find the corresponding literature. I think that I reported all the references in my presentation. So when the video will be available, you can find it, or I can provide the literature upon request. So you can mail me when you want and provide all the references.
All right. Next question. So this is about citizen science. From Moritz, how important is the camera angle or position for the plastic identification, in particular with regard to the integration of data from citizen scientists?
This is a very good question. We do know that the angle and position of and not only this, but also the resolution of the images. So the ground sampling distance of the image matters for the identification of the features. Of course, I have to say that the feature detection algorithms can be trained also to detect a plastic bottle, for instance, under different angles. So, of course, if the tool is trained only to zenithal view, it will perform badly under modified conditions. But the question in the challenge is exactly this: try to build a more flexible tools in order to allow citizen science to have less errors and to make usable the data that they could provide.
All right. So, well, another question is about discharge from Francesco. Well, I want to thank Salvatore for the interesting presentation. Considering river monitoring in terms of discharge evaluation to surface velocity estimations, I'm recently struggling about one critical aspect about flood conditions. Usually we applied velocimetry techniques under comfort conditions, but with flood conditions, many of the canonical steps are not possible. Like, for example, put some GCPs. There are many problems in orthorectification and the calibration of images. So the question, how can we handle, in your opinion, situation like during if I'm correct, correct me if I'm wrong, high flow discharge events, especially for making possible to obtain high values of discharge to enhance stage discharge relationships.
Okay, I hope I understood correctly the question. I don't know why the auto rectification in his case didn't work, but usually the question is, of course, the extent of the scene. So try to have a scene where we can clearly enclose fixed elements with the moving flow is critical, especially for the stabilization algorithm and ortho rectification activity. And of course, this could be an issue if the flood takes all the scene and my scene is not properly set, for instance. So if at the end of the day, the entire view of the camera is covered by water. In this context, this is true, this is an issue. I recommend to include in the scene for monitoring activity fixed elements like a bridge, for instance, that cannot be altered by the flood, hopefully, which can help in the authentication, providing a fixed element that could be included in the analysis. Then I don't know if I read especially high values of discharge, stage discharge relationship. Of course, this applies also for the river banks. So if we are interested in a stage discharge analysis, we need to ensure that over the entire flood event, we can detect the line of the water surface in my scene, which is not always the case. So the setting of the camera is extremely important. I see that I don't answer. There are other questions. Okay, there is another one. It depends also greatly on the setup you have in mind. Okay, this is a reply. Okay.
Yeah, I think going once, twice for the questions. If there's no more question, I guess let's just ask for final message from our speaker, and then we can go into the photo opportunity we mentioned in our email, and you can start opening your cameras. So last message from our speaker.
No, my last message is that I think that we are investing a lot in developing these techniques, and of course there is still a lot of work that needs to be done. We look forward for more collaboration in order to build and to retrieve information from different contexts where we can train our algorithms and improve the potential of our systems. I think that this can happen and is happening also thanks to the scientific society in which we relate, and that give us the opportunity to interact with a close community that is interested to one specific topic. And with acting as a community, we can certainly advance as one. So, and I feel that MOXXI is certainly a place where this can happen. Therefore, I really thank you all for participating to this webinar. I'm glad that there was such a large participation, and I hope to see you all in Vienna during our PICO session. That is also another opportunity to exchange idea and to have face-to-face interaction.
All right. So thank you for our speaker for today. If anyone wants to open their camera so then we can have a photo opportunity, let's do it. Well, it's okay. All right, technical team, are we ready? Well, because basically it's also the last webinar for the season. We'll announce in the future events and hopefully meet everyone in Vienna and create more projects together. So yeah, it would be nice to put faces on the names that have been with us since the beginning of this webinar activities. All right, again, thanks everyone. Technical team, let me know if it's okay. Okay, I'll count 1, 2, 3. Formaggio. All right, that's it. Again, thanks. Thank you for our speaker, our MOXXI chair,
Hi
Salvatore
everyone.
Manfreda.
Hi to the friends and participants. Hi Nick. Hi Francesco. Thanks for joining us. Hi everyone.
Yeah, and thanks everyone for coming, and see you in our next events. Bye.
Bye bye.